Welcome to IDS-IT. Let's explore an important topic shaping the future of defense and global security. I'm the founder and director of International Defense Security and Technology, a California-based nonprofit think tank dedicated to research and analysis on global defense, security, and emerging technologies. I also serve as CEO of Interplanix LLC, a New Mexico-based company advancing satellite risk analysis, orbital debris forecasting, and space security frameworks to ensure mission assurance and resilience. Previously, I served in leadership roles at India's Defense Research and Development Organization, DRDO. Most recently as Director of the Systems Analysis, Modeling, Safety, and Quality Cluster at DRDO Headquarters, New Delhi. This channel brings you deep insights into the global security ecosystem, from geopolitics and emerging military technologies to cyber, space, and system-level analysis of tech trends and their interrelationships. Subscribe and join us as we decode the forces shaping the future of global defense and human security.
Today's topic is the global race for space-based quantum sensors. Quantum sensors exploit superposition, entanglement, and matter wave interference to measure time, gravity, acceleration, and electromagnetic fields with precision far beyond classical devices. Put these sensors in orbit and their sensitivity increases. Longer free-fall times, lower environmental noise, and extended baselines enable measurements that are impossible on the ground. Space-based quantum gravimeters can resolve tiny changes in Earth's mass distribution, tracking ice melt, groundwater loss, and ocean mass transport with a resolution that sharpens climate models and improves disaster prediction. Quantum clocks in orbit will synchronize time at a new level of accuracy, reducing GNSS positioning errors and enabling navigation in GPS-denied environments for ships, aircraft, and deep space missions. Atom interferometer inertial sensors offer autonomous navigation by measuring acceleration and rotation against fundamental physical references rather than external signals. Cold atom experiments already flown demonstrate feasibility. MAIS-1 produced a Bose-Einstein condensate in space. The Cold Atom Lab on the IS proved atom interferometry in microgravity, and space cold atom clock experiments have validated the concept of orbital quantum timekeeping. These lab successes are now transitioning into engineering challenges, miniaturizing vacuum chambers and lasers, hardening optics against launch shock and radiation, shrinking cryogenic systems, and integrating robust control electronics that preserve coherence in orbit. The strategic stakes are high. The United States, China, and Europe led with active programs in quantum clocks, gravimetry, and atom interferometry, while India, Australia, and Russia are investing in niche capabilities and partnerships. Applications span civilian science and defense. Gravity mapping for resource and hazard monitoring, precise timekeeping for resilient navigation and communications, quantum-enhanced imaging and LIDAR for low-visibility sensing, and potential new detector architectures for gravitational waves and dark matter searches. Operational deployment will require constellations and integrated systems that fuse quantum outputs with optical, radar, and classical sensors, plus edge processing that turns raw quantum readouts into usable geophysical or navigational products in near real time. Technical and operational hurdles remain. Environmental sensitivity demands shielding and thermal control. Long-term stability requires advanced calibration strategies, and scaling to fleet operations requires reliable manufacturability and fault tolerance. Geopolitically, the quantum space race will reshape leadership in climate science, navigation infrastructure, and strategic advantage. As quantum devices move from demonstrations to satellites and constellations, they will redefine how we measure the planet and navigate the skies, creating new capabilities for science, commerce, and security. The coming decade will show which nations translate laboratory breakthroughs into operational quantum sensors in orbit, and those deployments will determine who sets standards and expectations for precision sensing in the 21st century.